So this video lesson is going to be about the difference between empirical and molecular formulas. So formulas are chemical formulas. We've been working with these since the beginning of this class. It simply communicates what atoms are bonded together within a compound. The difference between an empirical and a molecular formula is an empirical formula is the simplest, smallest whole number ratio of elements in a compound. So it's not necessarily how many are exactly connected and bonded to one another. It's more about the ratio of elements within the entire compound. So for example, in HO, it's a 1-to-1 ratio. There's one H to one O. NO2, there's one N to two O's, etc., etc. So that's not necessarily communicating how many are actually bonded. It's communicating the ratio of the elements bonding. The molecular formula is the straight up chemical formula. So that is how many of each atom are actually bonded and connected to one another. So what this means is a molecular formula isn't necessarily always an empirical formula. So you could look at a particular molecular formula, and I could ask you, what is the empirical formula of this? So what is the simplest whole number ratio of elements within the compound? So for example, this very first one, the empirical formula for H2O2 is HO, because that would be the simplest whole number ratio. The empirical formula for N2O4 would be NO2. And then for C9H18O3 would be C3H6O. So for example, I could give you like C2H6, and I could say, what is the empirical formula of this? So you would look at the numbers and say, can I simplify this down? If the answer is yes, the empirical formula would be that compound simplified down. Sometimes I could give you a formula and say, what is the empirical formula? And then it cannot be reduced further. So then that means the empirical formula just is the molecular formula. So for example, like NO2 is a thing, okay? But so is N2O4. N2O4's empirical formula is NO2. NO2's empirical formula is NO2. What we can do with this information then is we can determine empirical formulas from data. So for example, if we had an unknown compound and we decomposed it and we figured out that 82.8% of the compound was carbon and 17.2% of the compound was hydrogen, we can then use those ratios to figure out what the empirical formula of the compound is. One important thing to note is these percentages are simply percent by mass. So that's not necessarily how many carbon atoms there are, that's how much the carbon atoms weighed once it was fully decomposed from one another. Where's my iPad? What? Hang tight. Technical difficulties. Oh, I'm just going to stop the recording. We're back. Sorry. So, these percentages are percents by mass. So what we can do with these mass, we're going to start over. I'm sorry. Okay, let's dive in and figure out how many moles of each of these elements there are. So the key with this is basically, why don't you just assume you had 100 grams? Because if you had 100 grams and 82.8% of it was carbon, you had 82.8 grams of carbon. So if we assume 82.8 grams of carbon, and then assume 17.2 grams of hydrogen, we can then convert these values to moles using the molar mass. So the molar mass of carbon is 12.01 grams per 1 mole. For hydrogen, it is 1.10 grams per mole. Since we're just talking about hydrogen in general here, we're not talking about diatomic hydrogen. So you would just use the 1.01. So we can figure out the amount of moles given these values here. So 82.8 divided by 12.01, I'm getting 6.89 moles of carbon. I'm going to go ahead and do the same thing with the hydrogen, and I'm getting 17.0 grams of hydrogen. So, nope, not grams, moles. Why are we trying to figure out moles? Remember, 1 mole is equal to 6.02 times 10 to the 23rd. That physically tells us how many of each atom we have. And if we're trying to figure out the empirical formula, which is the ratio of the atoms, we should know how many atoms we've got. So now once that we've got these values, basically what we can do is we can use these numbers to figure out a ratio from one another. There are a lot of ways to math this. Here's the one that makes the most sense to me. Basically, I want to figure out a ratio between these. So what would be nice would be if these numbers were like 1 and 3. So that means for every 1 carbon, there's 3 hydrogens. Well, these numbers aren't nice. So then what we can do is basically just kind of simulate the same idea. So I'm going to take this 17.0 moles of hydrogen, and I'm going to divide that by the 6.89 moles of carbon. So if I do that, 17.0 divided by 6.89, I'm getting an answer of 2.46, but I'm going to round this up to 2.5. I'll tell you why here in a second. So basically what I just figured out is the ratio of hydrogen to carbon. So it's 2.5 H per C. Or in other words, for every 1 carbon, there are 2.5 H's. Now, can we have 2.5 H's? Absolutely not. So then what we can do is take this entire thing and multiply it by 2. So the empirical formula would be C2H5. That is the simplest whole number ratio. It's got to be whole numbers because you can't have half an atom, right? So even though the ratio is 2.5 to 1, you can't have 2.5 hydrogens. So that is why I rounded this number to 2.5. So basically, whenever you're doing these problems, you're going to be looking for like the nearest half or the nearest whole. So these numbers are going to play out to being a whole number, or they're going to be close to a half. And so you're going to use those values to then help you figure out what the empirical formula is going to be. So just a quick recap here. You take the amount of grams, you convert them to moles, that tells you how many of each atom you have, and then you determine a ratio of those atoms and then use it to develop the empirical formula. Given this example, I want you to go ahead and not try the practice problem. Instead, I'm going to ask you another question. So this question now says, if it is later determined that the molar mass of the previous compound was 58 grams per mole, what must its molecular formula be? So we figured out that the empirical formula from the previous problem was C2H5. So let's go ahead and figure out the molar mass of that. So that would just be 2 carbons and 5 hydrogens, which would come out to be 29.07 grams per mole. So that's the molar mass of C2H5. What this is telling us is the molar mass of the actual compound that we decomposed. What we're actually trying to figure out was 58.00 grams per mole. So now what we can do is figure out a ratio between these. So the molecular molar mass is the 58.0, so that's like the actual one. And then the empirical molar mass is 29.07. That is the molar mass of the compound we had figured out previously. So if I take these and divide them, I'm getting 1.99, round to the nearest half or whole, 2. What does that mean? That means the molar mass of the molecular compound is 2 times heavier than the empirical. Well, if the empirical here is C2H5 and the molecular is 2 times heavier, well, the molecular must be C4H10. It must be twice as heavy as the original. Now, given these example problems, I want you to go ahead and try this practice problem on your own. So I encourage you to pause the video, give this a shot, and then tune in when you're ready. All right, here we go. So note that the first thing I did was I took these values, these percentages, I put them to grams, and I converted grams to moles. So then I knew how many moles of each compound I did. Again, lots of ways to do this. The way that personally makes the most sense to me is I took the smallest mole value, because clearly if that's the smallest mole value, that's the element that has the least amount within the formula. And then I divided the bigger values by that smaller value. So when I did that for the sodium and the phosphor, I got the number of 3, which basically means there's 3 sodiums to 1 phosphor. When I did the same thing with the oxygen, so the smaller number divided by the oxygen number, I got 4, which means there's 4 oxygen per phosphorus. So 4 oxygen per phosphorus, 3 sodium per phosphorus, I got out Na3PO4. I specifically put the elements in this order because this is sodium phosphate, an ionic compound, and metals are always listed first, and then PO4 is a polyatomic ion phosphate. So you might not have seen that initially, but that would be like the correct way of writing that out. And then for the next problem, you compare the 2 molar masses. So this molar mass was the molar mass of my empirical formula. And it just so happened in this example that the molar masses were the same, so that means the actual compound, its molecular formula is sodium phosphate, Na3PO4. So in this case, the empirical and the molecular were the same, which can be the case. If you've got any questions, please reach out. Great job. Oh, skip that. Don't do that. It's not happening. Cool. Good job.